Okay, this video is for Class 12 of Environmental Engineering 670. This lecture is taped for April 10th, 2019. Before we get into the material for today, let's go over a couple of announcements. First of all, the first WMS related assignment, homework number 10, that is going to be due a week from today, so you should upload it to MU Online before 4 p.m. on Wednesday, April 17th. Next week's class period, we'll be back to our live meetings, and so although this lecture is recorded in advance, next week's lecture will be live. And then just looking a little bit further into the future, you've already submitted part 1 of the project, which is kind of your literature review, where you're doing a little bit of evaluation of the information that's available for your report. Well, the whole report, the final part 2 version, is due before our exam. Our final exam is Wednesday, May 8th, and so that's when you need to turn in the project. If you have any questions about the announcements, please send me an email, stop by. I'd be happy to go over it with you. Okay, today we're going to continue our look at WMS, the Watershed Modeling System. In class last time, we just did some of the basics, learning how to navigate through the wizard in order to delineate a watershed and obtain some of the data that can be obtained through the WMS workflow. Today we're going to actually start doing a little bit of watershed modeling with the tool, and we're going to start with the simplest watershed model, the rational method, and work our way through a couple of other activities: national streamflow statistics, TR-55, taking a look at more detailed land use and soil type data, and then finally culminating with the automatic calculation of curve numbers. I'm going to email you a couple of files that you're going to need to go along with today's activity. First of all, there's a handout, excuse me, a handout that kind of loosely follows the procedure that you'll be seeing on the screen. Because the program is always changing, then that kind of forces me to update what I do on the screen compared to some of the initial instructions that I put together on the handout. But hopefully, at the very least, it just gives you a rough signposting idea of what the main tasks are that are being accomplished. My idea is what I'd like you to do is follow along with the video. So watch me going through the activity at the same time that you yourself do it in WMS. And so you can simultaneously kind of just mimic what I'm doing, or even work ahead as you get more acquainted with how the program functions. For one of the activities, you're going to need an elevation data file. So that .gdm file that I emailed to you, there's a way of exporting your elevation model from WMS so that it can be opened without having to go to the web. And so I just wanted to show you how to use that functionality, which is why I provide that GDM file. And then finally, there's a translation file that I gave you in class last time that helps you to relate curve number, land use, and soil type. And so I'll also include another copy of that just for you to have it as a reference. So there are 4 activities that you'll be working through in today's lecture. The first, just a review of delineation, which is what we did last time, and then moving on to the watershed modeling. Looking at national streamflow statistics, which is kind of an interesting approach, TR-55, which is maybe where we're starting to get a runoff hydrograph that is a little more sophisticated than we can get from the rational method. And then finally, how do we automate the calculation of curve numbers? It's kind of a neat process. These 4 activities will kind of be setting us up for next class period. We're going to do some HEC1 modeling, and that is where we'll leave it with WMS. So in total, it'll be 3 lectures. We're going to use WMS. So let's go ahead and get into it. Just as a reminder, the majority of this video is recorded in a previous class meeting, so there may be some references to times and dates and assignments that don't quite exactly match up with what you have before you. So the announcement slides that I've showed you already, those are the ones that govern for our course. If you have any uncertainty or questions related to the material, please just let me know. I'd be glad to go over it with you.
If you'd given me some advance notice, I could have maybe brought one in today, but I didn't.
I'll be good for
Okay. So if you drop your outlet like on the main stream or too close to it, then it'll delineate like the entire contributing area. So you got to be maybe 1 or 2 blocks away from the main stream that's running along Blue Sulphur, because what we want to do is we want to get the stream that's running along Liken's branch before it gets to Blue Sulphur. So see, this stream we know is on the west side of Blue Sulphur, so we're sizing the culvert that's passing the water from the Liken's branch watershed under the Blue Sulphur road. So, you know, pixel placement in this case can have a pretty big effect. So what we're looking for is your watershed should be on the order of about 265 acres. And that'll vary slightly depending on what DEM resolution you chose. I chose the 7.5 meter DEM. I think the default, based on how far you're zoomed out, probably it suggested 15 meter resolution to you. I'm always a little bit like, well, I'll just take a little more time and go for slightly better resolution. So I'm just curious, for those of you who chose the 15-meter resolution, what did it choose? What did it say the area is? 263, 262? All right. So in the magnitude of things, we're talking far less than a 1% difference, and so it's probably fine. And we've got enough relief, there's enough topography in this area that we're probably okay with the coarser resolution. Where it really matters is where you have relatively flat terrain. That's where it's really important to have the finest resolution, but it being so hilly here that probably we'd be all right with the 30-meter resolution. All right, so we have our watershed delineated, and remember how we could trim the DEM, because I've got a lot more elevation data there than I actually need. And I'm going to turn off the street map now too. So I'm just going to disable the street map, and I'm going to trim that DEM by right-clicking up here under terrain data, the active elevation model, and trim with a polygon that I interactively just draw around the border, double-clicking at the end, and then it trims away that. And so I can zoom to the extents. Let's see. And remembering to frequently save, because it could crash. Yeah, I don't know. There used to be a button that would view. I don't know where the zoom extents button is. Just got to do it manually, I guess, for now. All right, so we've got this watershed, and here's what we know about it. I've got the instructions on the handout I've given you. We're going to go into the hydrologic modeling module. We haven't done much in there yet. It's this button across the top that the reason it looks the way it is when you actually prepare the schematic of watersheds. This is different watersheds feeding into various outlets. And so across the top, click on the hydrologic modeling module. Okay. Mm-hmm. Mm-hmm. Yeah. Yeah, go back into the wizard. Okay. And here under choose outlet locations, there's delete outlet point. And I think if you move that out of the way, you can click that. Yeah. Okay. Yep. Mm-hmm. All right. So we're in the hydrologic modeling module now. And over here on the left side, the context-specific menus have changed. And what we want to do is use the Select Basin tool. Right now, by default, it's on Select Outlet. But click on Select Basin. And you can't see it because the text is right on top of it. But there's a symbol there. They put it at the center of the basin by default. What we're looking at is kind of like a schematic of a watershed. And so if I turn off everything else, it's saying here is a basin that goes to an outlet. That's this model, is some basin that's connected to an outlet. And so if you double click on that basin, oops, right now by default it assumes we're going to do a HEC1 model. So we need to change that using the drop-down box to rational as the model. And now, still under Select Basin, we'll double-click on the symbol for the basin in question, and you'll notice that it's already filled in some of the data here. Remember, the rational method is Q equals CIA. So WMS is acting as a preprocessor. It's going out into the world, and it's finding all the data you need to satisfy the questions, what goes into Q equals CIA. So the area here is automatically filled in. The runoff coefficient, let's just assume that we've been out into the field and we've observed the watershed. We're familiar with the type of vegetation that's there and the soil that's there, and so we decided that we're going to use 0.6 for the runoff coefficient. Now, runoff coefficients are inherently kind of squishy, and it's not really reproducible and defensible in the same way that curve numbers will be when we automatically calculate curve numbers using land use and soil type data. So there isn't, in other words, there isn't a way to automatically calculate a C value. So we just have to be aware of that. It's just by double clicking here on the basin using select basin tool. Oh, see, originally it was like this. The basin was behind it. And so when you're on the select basin tool, you single click on it and you can move it aside. Or you could turn off the text. The other way is by turning off the text. If we go here into the display options, you can go into drainage data and just uncheck all of these labels so they're not in the way any longer. Okay, well. The street map?
Yeah, well, not the street map, like the...
Oh, you're talking about the elevation? Yeah, it's here under terrain data. You can click it on and off.
Okay.
Yep. Okay, so what we need to do is bring up the rational method details. Has everybody got this open? Yeah. Okay, so remember what we said is we're going to have a runoff coefficient of 0.6, so key that in. Now the time of concentration, it can calculate that based on basin data. So here, compute T sub C based on basin data. And it brings up some different ways of estimating the time of concentration. And so what we're going to use is, let's switch it here. Instead of saying time of concentration, there's a formula for lag time. And lag time and time of concentration are related to each other by the fraction 3/5. And so if we know one, we can calculate the other. But the SCS method, if you switch it to compute lag time and then go down to the SCS method, it has automatically filled in all of the things that we need to use the SCS method to calculate lag time, except it doesn't yet know the curve number. So when we start getting land use and soil type data into WMS, it would automatically calculate that as well. But let's just manually enter that in. So you'll notice it's calculated already the watershed length. It already has the watershed slope. But the curve number, we're going to have to enter here in the variable value box. So in the handout it says, let's assume a typical curve number would be 75 for this area. And so as soon as you enter 75 and then browse to another location, then it calculates the lag time for this watershed based on the formula that's shown. It summarizes here in the window what's the lag time formula for the SCS method, and it's using this lot length, this curve number, and this slope. And you could override those values if you happen to know that there maybe is some problem with your data and you want to adjust it. But in our case, the watershed lag time is going to be 0.26 hours. Okay, and then when you click OK, it copies that 0.26 hours. It converts it to minutes. Did it though? 0.26. Oh, okay, yeah, that was lag time. So it converts it to time of concentration, right. So that's why here the T sub C is 25 minutes, is because time of concentration is 5/3 the lag time. So it converted that lag time in hours to time of concentration in minutes. Okay, so now we need the rainfall data. So compute IDF curve. So if you click on that, then it's going to go and get the data that we need for this location. It's set to Hydro 35. If you click Get Online Data, it should go to the precipitation data frequency server for us and go and pull the rainfall data for our watershed. So it's like it knows the location in the world, and it goes and gets that IDF curve and imports it directly. So if you think about it, that's pretty slick compared to like Bentley when we had to kind of manually type that in after we got the data from the website. So that's kind of nice that it does that. If it doesn't, you can always define the storm data yourself in the same way that we did with like in the homework assignment where you use the 2-year and the 100-year and it kind of interpolates in between. So it could do that interpolation if you went and manually got the IDF data for the location. But so it's got that for us. And so what we need to do is compute the intensity. So you select like the 10-year curve in our case. So you just select the row for the 10-year, compute intensity. So based on the time of concentration that we previously calculated of 25 minutes, it's extrapolating between the 15 and the 30 minute. And so if we look, we can see it's going to be somewhere between 4.28 and 2.97. And so it already extrapolated based on the time of concentration. So it's going to be an intensity of 3.22 inches per hour. And you say done, and it copies that intensity here. And so now we have the peak flow rate. See how in the window it's saying the flow rate would be 515 CFS? And yours will probably be slightly different if you had a different area, but probably not too much different. Now the final thing is we can have it compute a hydrograph. And if you click on that, just move the window to the side before you click on compute hydrograph. So click compute hydrograph and just use traditional method for routing. That means if you're combining multiple watersheds together, how long should the travel time and the delay through the stream be? In this case, we just have a single watershed, and so we don't really need to account for a separate delay as the water travels from one outlet to the next. So just use traditional and click OK. So after we click compute, it brings up this hydrograph that if you double click on that, we need to close this. Double click on the hydrograph, then it shows you traditional triangular shape that's associated with the rational method. So it just goes up to the peak, and then it immediately declines back down to 0 flow rate. And that's the rational method. It typically overestimates. If we're going to do a more sophisticated analysis of this watershed actually using land use and soil type, it would probably be less than this. But they talk about sometimes all you need is just a rough estimate. And we've essentially delineated the watershed, and we have calculated the time of concentration. We obtained rainfall data, and we estimated the peak flow, and it only took, well, about 20 minutes, 25 minutes. And so now if all you need is a rough estimate, and they're looking at a culvert, and it's a 3-foot diameter culvert, and they're just wondering, oh, what's the peak flow rate going to be, then you'd be able to really quickly say around 500 CFS, ballpark. So that's the value of the rational method. So let's save this so that you've got it as an example of a functional rational method model. So you click Save, and wherever you indicated as the location for saving, it's created now a couple of different files. Oh man, Windows File Explorer is just wrecked on this machine. Same as the other classroom I work on. Anytime I want to browse files, it's not doing so great. So, all right, so that's the rational method. What we could do is we can add an additional outlet and break the watershed up into parts. And so if you turn the page, I show you that there's a couple of other spots where what we're going to do is subdivide this watershed into smaller pieces. And so I'm going to, by the way, I'm going to delete that hydrograph that's there right now. So there's this button on the left, Select Hydrograph. And when you've got the hydrograph selected, if you just push the delete button, then it doesn't delete it. No, wait. I thought it did. Oh, okay. Well, it used to. Let's subdivide the watershed. I'm going to turn the map back on. And what I want to do is break it up into different pieces. And so where I'm going to put those new outlets, now you can go through the wizard, or you can go into the drainage module, and you can create outlets with the tools that appear over here on the left side in the drainage module. So you could go back into the hydrologic modeling wizard and choose outlet locations and create outlet points. But a lot of these same tools that are available through the workflow guidance of the wizard is available in other places too. So here under the drainage module, what I'm going to do is I'm going to create outlet points here and there, and then I'm going to delineate the watershed again. So I'm going to go into the hydrologic modeling module, and once I've dropped those two additional outlets, click on Delineate Watershed, and it warns you that it's going to delete everything that was there before as far as the data of the area of the watersheds and so on. All right, so what it's done now is it's calculated subbasins. Even if it's not turned on, the DEM data is still available to the computer. So remember, I wasn't displaying those contour lines, but it was still there in the background so that the computer could go and get the data. So, you know, maybe there are some reasons to subdivide the watershed. You know, the rational method works best when you have relatively small basin sizes. It's not really applicable for a watershed that's 300 acres. But its performance is better for relatively smaller watersheds. And so if we have 3 subdivided watersheds and then we model them separately, like maybe we know that this lowest basin is the most urbanized. So if you turn onto the second page of the handout, I've given you different C values and curve numbers. So if this has more houses and we assume it's going to be more impervious area, then we can get an accurate idea of the watershed as a whole by using different C values and different times of concentration for each of them. So what you can do is go back into the hydrologic modeling module, and once you double click on one of the basins, it will allow you to, we can do all of them rather than just the selected. So here under show, you can do either selected or all. We can expand this. And so the lower basin, maybe it helps at this point to rename them. So 4B, that's the one that I'm referring to as the upper left. And basin 5B is my upper right. And then 6B is the lower basin. So in the handout, what we have is different runoff coefficients for each of them. So the upper right, for example, I'm going to use a runoff coefficient of 0.55. The upper left, 0.40. And then the lower basin was the one that's maybe more highly urbanized, so I use a higher C value, 0.70. Mm-hmm. Are you looking at the outlets under type or basins? All right. Yeah. If you double click on an outlet, then it'll bring up this model in terms of the outlets rather than in terms of the basins. So when you have the 3 basins shown, you can change the runoff coefficients, and let's calculate the time of concentration using the basin data. So you'll click compute, and you'll have to scroll down to lag time, SCS method, and then put in the curve number for each of them. Now, right now, I'm working on the upper right basin. All right. So the upper right basin was the one that had 75 for the curve number. And that allows me to calculate now the time of concentration is defined. Yeah, there it is, time of concentration. All right. Now, upper left. Lag time, SCS. Upper left, 0.70. And lower basin. So when you subdivide the basins, it becomes a little bit tedious. Now you have to do everything 3 times. You have to calculate the time of concentration 3 times. You have to do the IDF curves 3 times. So compute intensity. For the time of concentration, you go to lag time, SCS method, and then you're going to have to enter in the curve number. So this one, which one did I just do? Upper right. So upper right, lag time, SCS, upper right was 75. Why are the intensities different for all of these 3 different basins? The C value doesn't affect the rainfall intensity. That's right. It's because we have different times of concentration. And the worst case scenario is a storm duration that lasts exactly the same length as the time of concentration. So that's what it's picking up on, is we've calculated the time of concentration for each of these watersheds, and then it's finding the intensity that's going to correspond to the maximum flow that comes out of each of the watersheds. So now, if I've done things right, then what I should see is out of the upper left, flow rate of about 140 CFS, and that's what I've got. 143 is what it's coming up with. And it'll vary a little bit depending on where you drop that outlet, because that's going to affect the area. The lower basin, about 210 CFS. The upper right basin, about 220. So, you're not what? Okay, change this from outlets, change it to basins. All right. Now, I think you may have more. Okay. Did you have an extra outlet someplace?
I think like right.
Yeah. So it's so close to a border that what it's done is it's split the. You have to kind of go a little bit away from where streams junction. So it's close enough to a border that it's picked up a 4th watershed. And that's okay. It's relatively small. It's only 0.39 acres, so you can kind of just ignore that one. So if you go back, if you open up that dialog again, so you use this and double click on one of the basins, and then leave it that, but then all, yeah. So you have to keep track of which one is the small one and just ignore that.
Okay.
Okay. Can you zoom in? Yeah, just right on there. Okay, and let's turn this on and see what we got. That should work. And those are both outlets, right?
Mm-hmm.
Let's calculate Topaz again.
Okay.
See if maybe that helps. Now, all right, so what it's saying is that you've got some outlets there. Oh, that one. You can't have an outlet just in like a random spot. So zoom back out again. That.
Oh, I see.
So you need to delete that, and then you'll be able to do it. So for each of these activities that we have today, you have the list of instructions of like what to click on and in what order, and I'd encourage you to practice this. You know, like find some watershed that you're interested in and practice making a rational method model for that watershed, just so you can cement in your mind what is the workflow that you need to do it. This hurricane DEM file.gdm, and we're going to save WMS, save what we were doing, and then create a new project and open up that DEM file. So browse to the location that has hurricane. Where did I put it? C temp. All right, there it is. Hurricane DEM file. And then it just loads that elevation model already clipped. It's the watershed that we're going to look at is enclosed inside of it. Okay, so basically what I had done is downloaded it through the online data, and then I trimmed it, and then I exported. You know, once you have a DEM model, you can right-click on it, and there is Save Digital Elevation File. So, you know, different pieces of your model will be automatically stored when you save a WMS project file, but if you want to like spin out just a piece of it rather than the entire project altogether, you can kind of like export the digital elevation file. So that's what I did. So what do we do at this point? If we want to delineate a watershed, we have the elevation model. What's the next step? That's right, Topaz. So Topaz is what is going to be analyzing every pixel and figuring out which adjacent pixel is lower, because that's the direction that the water is going to flow. So it kind of just for each cell is identifying a flow direction. So we go here into the wizard and we do compute flow directions and accumulations, so Topaz, and you compute Topaz. And this may take a while because it's a pretty big DEM file. Oh, this one's fast. Faster processor than my office computer, I think. And then what it'll do is it'll show all these flow accumulations where there's at least, in this case, 5 acres upstream. Okay, so close this and zoom in on the left side of the watershed, because you can look at like what direction is the water flowing. The water is flowing to the west. And so here's the main stem of this watershed. And this is just some smaller watershed here. And let's change the flow accumulation just to get a feel for what are the mainstream and what's just like the side streams here. So let's change it to 100 acres. and apply to display. Now you can see, all right, this is the main stem. Let's change it to 200 acres. Apply to display. And doing that will help you pick the right spot to put the outlet on, because before, like if we had it 3 acres, it's less obvious where we're going to be putting the outlet. You know, I could accidentally click here thinking, well, that's to the left, but that's not the real outlet. Like the stream that we want to delineate is the one that has a lot of upstream area. So all those minor ones kind of don't show up anymore when you change the accumulation threshold to a higher amount. Okay, so the next thing is we're going to create an outlet point just here, almost to the limit, but not all the way. And once you've dropped the outlet point, delineate watershed. And it'll go through the process of following the ridge lines. And it's calculating. You can see it's kind of going slowly here to calculate the maximum flow distance. What it's doing is, remember when I dropped the little blue stream thing and it shows you the flow path? I showed that in a previous class period where you can click somewhere on the map and it'll show you what direction the water is actually flowing. Right now what it's calculating is it's doing that for every cell in the network, and it's calculating how far is it if a raindrop falls here to the outlet. How far is it if a raindrop falls here to the outlet? And it's just going through that one cell at a time for the millions of different elevation points that we have in this watershed. So that's why it kind of takes a while. Probably I have more resolution, more elevation resolution than I really need considering how big this watershed is. If I'm not mistaken, this is a, the spacing was the 7.5 meter resolution, and what we've got is like 50,000 acres. So this is a really large watershed. So it's far too big to model with the rational method. But if you want a quick and dirty, kind of just a real rough idea of what the runoff is going to be, we can use national streamflow statistics. And so we have the watershed delineated, and what we can do now is go here into the drainage module. So it's, remember these buttons across the top, the drainage module, and okay, let's go into the hydrologic modeling module first and switch the drop-down box to NSS. This is where before we had chosen rational method. This time we'll do NSS. And in West Virginia, there are 3 different regions that the USGS has, they've done like a statistical analysis of streams using stream gauge data and rain gauge data. They've kind of looked at about 100 different watersheds in the state and extrapolated the relationship between watershed area and peak flow rate. The region that this watershed is in is a region that's called the Western Plateaus. So double-click on the basin to bring up the dialog box associated with national streamflow statistics. It's that double-click before that we used to bring up the rational method window. This time, though, because the drop-down box is on NSS instead of rational method, when we double-click on the basin label, it brings up a slightly different window. So I'm going to pause for a moment and make sure that everybody's on the national streamflow statistics. So change it from Alabama, so scroll down to West Virginia, and then there's a publication that USGS has put out. It's like 110 pages long for the state of West Virginia, where they show all the calculations they went through to determine what area and what peak flow rate you can expect to see. So it already knows the basin area. So here, see how it says 80 miles, 80 square miles? That is the area that it got from us delineating the watershed in question. So it's put that area down here into this formula, and scroll down to, we want to have the peak flow Western Plateau.
Why would my area only be
7 square miles? It might be that your watershed outlet is in the wrong spot. Could be that your projection is off. Yeah, it's because, see how you're in feet right now? The watershed model was in, yeah, it's the projection issue. So you need to go into the, for some reason it didn't remember that you're in zone 17. All right. Yeah, so I guess it's kind of worth checking. It usually remembers what zone you're in and what projection and so on. But if you're in feet and the DEM you're bringing in is meters, then the areas it calculates will be wrong. So what we're looking for is this peak flow western plateau, and we know the area. And so click on compute results. Let's see. So select that and compute results. And now what it's done is it's calculated for instance, a 5-year storm. What's the peak flow? About 5,000 CFS. For the 10-year storm, the peak flow will be about 6,200 CFS. So of the list, you have to click over here to make it a selected location, and then you compute the results. And all it's doing is it's just a regression equation that is based on the area. So this is only valid for watersheds that are mostly rural. If you have an urbanized watershed, or if you have like a dam or any kind of like reservoir flood control structures in here, like if you have a lot of places where people have ponds on creeks and so on, then this won't give you accurate results. It talks more about what these NSS equations are if you get the publication for the state in question. But so this is just another way to really quickly come up with an estimate of what the peak flow might be for a certain return period. You can see this goes all the way up to a 500-year storm if you scroll down through the list. So 500-year storm, we'd maybe see around 14,000 CFS. So you probably wouldn't make a culvert to pass that flow. But. Yeah, I don't know. That's an interesting question. I'm not sure what they mean by equivalent years. I'll have to look into that and get back to you, because I'm not absolutely certain. Yeah. I don't know. I guess we could always click help and see what comes up. Equivalent. Yeah, I don't know. Yeah, it might be related to the range of the standard deviation. That could be it, you know, like where the error is 30%, and so it could be that the size of that error is 8 years or something. I don't really know. It doesn't seem to hold, though, if you look at 36% standard error for the 500-year storm. Yeah, I really don't know. I'll figure that out, and I'll report back on Thursday. Okay, so let's say that we want to export this results into Excel. So you see that that's one of the options here, export. That's one of the things that WMS is pretty good at, is preparing the data so that you could analyze it in another way. So let's just find a folder that I'm going to be able to find this again. So it's called NFF export, National Flood Frequency Export. I'll save that and then try and open that up in Excel just to see what it gives me. So it's that same table that we were looking at where it has the return period. It's got the peak flow rate, the percent error, and then this mystery column, the equivalent years. But it's basically just a report of your analysis where we've got the drainage area, it's got the 80 square miles that we know, the state that we picked, which peak flow region we're in, and so on. So there's 3 different geographic regions that the state is broken down into. And the other options, if we scroll down a bit here, there's the Central Mountains. So the Central Mountains would be like Beckley, Cranberry Wilderness, that sort of area. And then the Eastern Panhandle is just totally different geography because it's really flat out there. So they have a different national streamflow statistics equation for the Eastern Panhandle. And then these other ones like east, north, south, and so on, that's just old methods that have been replaced. The most recent publication, I think, was the 2010 publication. And so that's the best one we've got for really just empirically predicting what the runoff is. All right, so save this one so that you have a national streamflow statistics. So we'll say NSS example. Maybe should have saved that earlier because you never know when it's going to crash. And let's do TR-55. Now with TR-55, we're getting into the territory of that's actually the model that they run over at the Division of Highways for some of their smaller watersheds. You know, they wouldn't necessarily just use the rational method because you can do TR-55 quickly enough that there's no sense in using an inferior method when the preprocessor can set everything up so easily. So create a new project and make sure you're in zone 17, units of meters, and use the wizard to delineate the watershed that's shown on the image I've given you. So the best way to figure out if you're in the right spot is look at the highways. The highways can give you an idea of like the geography and how far you need to zoom out. Now, I'll be doing it on the screen so you can watch me, but I'm not going to talk through it. I'd like you to delineate that water, to find the outlet and delineate the watershed, and then we'll come together and go through the TR-55 part of it together. It's easy to accidentally get too big of an area. That's what I did. My Topaz finally just finished. It took 25 seconds, which is an an eternity in Topaz years. So this is the watershed that we want to delineate. What's the name of this road? Garrison Avenue. Anybody know where that is? I don't. Yes, correct. So we're going to delineate this watershed just before it goes under the interstate. That is our point of interest. Hard to believe that just a week ago, it was just program crashing, nothing was working. Finally, we're doing stuff. It's beautiful. All right. So about 980 acres is what we ought to have. And of course, you can trim that DEM if you want to throw out the stuff that you don't need. I'm going to trim my DEM here. Oops. Go into the hydrologic modeling module, and this time, instead of, we're not going to do rational, we're not going to do NSS, we'll do TR-55. And so now it knows it's doing TR-55 so that when you use the select basin button and double click on that symbol that's hiding back there behind the text, double click to bring up, it has the TR-55 modeling dialog box. And so just like before, there are certain things that it can go and calculate based on the data that you have in the background. So for example, right now it doesn't have the time of concentration. So let's fill that in the same way that we did when we were using the other methods. So you can click Compute under Basin Data, and let's use the SCS lag time method. So change computation type to lag time, scroll down from Denver to SCS. And let's assume that the curve number in this watershed, instead of 90, it's an odd default, 68. And the other stuff it already knew based on just the elevation model. So 68, so it comes up with a time of concentration of 1.1 hours approximately. The drainage area it already knows. Now what we have to do though is put in some rainfall data. So let's change it to rainfall distribution. See where it says type 1. Temporal distribution, we live in a spot that has type 2. So we need to change it to type 2 because that's the Midwest. And then the rainfall depth that we want to figure out is from the precipitation data frequency server. I'm surprised that there isn't a way to automatically obtain that. So we'll actually have to go to the precipitation data frequency server. It surprises me that that's not automatic. All right, West Virginia. What we want to do is find the 25-year rainfall depth nearest to the time of concentration that we already have. So we have about a 1-hour time of concentration. So let's go with the cursor on Charleston, go down here to the table. The 25-year storm is this column. We want the 1-hour depth. So This is a depth of 2.13 inches for a 1-hour storm, 25-year return period. So 2.13 inches is what we'll put in here for the rainfall. You know what? No. That's not supposed to be the, we need to use the 24-hour storm depth. Now that I'm thinking about it a bit more, I'm pretty sure it's supposed to be the 24-hour storm depth because it's using the type 2 distribution, which is a 24-hour period. 4.16 for the 24-hour storm? All right. So put in 4.16 for the rainfall. 4.16. We've got 1 minute. All we have to do is click Compute Hydrograph. And now, it's not that stupid triangular hydrograph that we had for the rational method, but this is a hydrograph that maybe is a little more realistic because it's the 24-hour distribution. Now, why don't we have any like no runoff for so long? It's because the 24-hour storm, remember, assumes that there's very little rainfall at first, but then there's this sudden period where most of the rain is coming. So this is a 24-hour runoff for a 24-hour rain. No, it definitely matters. Probably that. Yeah.
So it's recommending that just.
Yeah. I mean, it'll usually, if you go one step finer than it recommends, then that's conservative. You know, you're better to be safe than sorry. It'll take a little bit longer. Yeah.
I went to download the area.
If you look at your coordinates, something's off there. So what I do is start over and begin a new project. Well, first go in here and see if you can define bounds. Change it to, for the datum, do the bottom one, and then change projection. Like kind of setting it again would maybe, if it's not quite sure on what the projection is, overwrite what it was doing before. So choose from the library. Okay, UTM zone 17, okay, and accept that. Okay. And then now you can define the bounds. I think maybe it wasn't seeing the bounds, so you can, okay, yeah. Click there and back again. All right, now you can go next. Yeah, that's good. Mm-hmm. How many? So somebody asked the question, you know, like what DEM resolution should you use? And usually it's going to suggest something that will allow it to calculate Topaz pretty quickly and do the delineation pretty quickly. And so usually, like, I think about how much time am I willing to invest. I'm usually willing to go a little bit beyond what it suggests. And so if it suggests 60, I go with 30. If it suggests 30, I'll go with 15. But, you know, there really is no right or wrong answer. It's just kind of a trade-off between how long are you willing to spend to download the data. Does your computer have the RAM to keep it all in the memory? You know, I probably could have done this at the 3-meter resolution and it would end up working just fine. But, you know, if it becomes too coarse and you see really jagged edges, like if you look at the blockiness of the outside perimeter, sometimes that can give you an idea of whether things are okay or not. You know, like if it is, if you know that there's a little bit more detail in the shape of the hill than the blockiness of the DEM is able to capture, then you might want to step down a level and improve the resolution. So once you get the DEM in there, you can trim it to throw out the stuff that we don't need outside the watershed. And maybe save your work in case it crashes later. All right, so once everybody gets the watershed, then we're going to load in the land use and the soil type data. So I'm going to wait until then to show you how that'll change things. What we're going to do now is we're going to load in the National Land Cover Database and Surgo. And so if you go back into the wizard and download data, so we already have the elevation data, so unclick that because we don't want to download that again. But do check NLCD, that's the National Land Cover Database, and we've looked at that before. We pulled it up on Google Earth Pro, where we were just loading in what areas are impervious, what areas are, you know, deciduous forests, what's cropland, and so on. That's the type of data that's in the land cover database. Then also scroll down, and we want the soil data. That's the Surgo soil data. Now, for whatever reason, WMS in the past hasn't been real good at picking out the right Surgo soil data, and it'll actually get way more than we actually need. So after we download this data, it might start displaying it at a view that is really zoomed out. So our project view is going to change probably. Excuse me. So just once you have those two things clicked, then select download data from web and just use whatever default assumption it wants to give you for the raster size. That is it's trying to suggest a size for each cell in the land cover database. So just use the default. You can see it's downloading the soil data. It'll get the land cover data, and then over here on the left side, now it's changed the project view. So we're looking at two separate things. First of all, I'm going to switch off the street map. So these black polygons are the soil data, and I can switch it off down here. So you can see that since my view covered two different regions, it downloaded both of those regions' soil data. So it may be that my watershed it looks like the entirety of my watershed is just in the 611. It downloaded the 77 because part of my view extents went into the 77, but I don't need the 77. I only need the one that's covering my watershed boundary. So here's my watershed boundary, and when I click on the 611, the soil data from 611 covers the entire boundary that I need. So I'm just going to right-click on the 77 and delete it from the project because I don't need it at all. I can turn on the 611 again and it's there. By the way, this is a good time to save your work again. So if you just click on the Save button, then all of these things that we're working with are saved in the same project directory. The TIFF file, that is the image that's in the background, and you can see it's created an image version of this land cover database. So that's what this TIFF is it's the colors that we've seen before. But also here it's loaded it as a land use into the grid. So it's not showing up, but that data is there in its memory. So what it's actually going to look at to try and figure out what land is in what location is this land use grid. So if I turn that on, then you can see this is kind of, each of the colors represents a different type of land use, but the image version of it is also loaded in the GIS data. So what do you think red means in this view, the GIS data TIFF file? Buildings, yeah, built up areas, right, good. Blue is water, green is plants, and different shades of green mean different types of plants. If you go to MU Online, there's a folder here called WMS items, and you need to download something that's called the CN table file. So if you just click on it, it's just going to display the text, but what you want to do is right-click on it and do Save Target As, and then browse to a location that you're going to be able to find. Here I'm putting it in my WMS Day 3. So that curve number table, you can open it with the notepad if you just want to look at what's in there and if you wanted to edit it. You need to display all files because it's not formatted as .txt, but the curve number table, all it really is a text file. And so what it's showing is these numbers on the left side. So number 11 is what open water comes up as in the National Land Cover Database. 11 is open water. And so then these four numbers that follow is the curve number associated with open water for type A soil, type B soil, C, and D. So water doesn't make much sense, but then if you look at something like deciduous forest, so color code 41 in that National Land Cover Database, if it's in soil type A, it's going to assume a curve number of 30. Soil type B, it's going to use a curve number of 55, and so on. So later on, we're going to load this file in as kind of like a key so that Excel knows those polygons of soil type overlaid on top of the raster file that's the land cover, what curve number should it assume for each one of those intersections. So download that so you've got it available. All right, so what we've got is the land use, and we've got the soil type, and we're going to use it to calculate curve numbers. Everybody have it so far? All right. Yeah, you mean like, can we trim the soil? Mm-hmm. Yeah, we'll do that. Although this doesn't take up too much data, not as much as you might expect, because each one of these polygons is a vector rather than a raster. So vector files usually are more compact for a certain area than an image file would be. All right, so let's start with the soil type. We've got some instructions here under the bulleted list. Let's just go through them one at a time. So we've deleted the one that we didn't need. All right. The first step that we have to do once you've deleted that other shapefile that wasn't supposed to be there, right-click on the 611 file, and one of the options here is Join NRCS Data. Does everybody see that? If you right-click on the soil 611, then one of the context-specific options is Join NRCS Data. So what that's doing is right now it doesn't know for each one of these locations, it doesn't know what soil type it is. Like we can select the properties, and what it's popping up is if you just click one of these polygons, it's telling us what area it's in. So it's in West Virginia, soil file 611. And it has this soil key. And you remember seeing those 3-letter abbreviations when you did the assignment having to do with like an area of interest. So it knows that soil key information, but it's not automatically pulling up the hydrologic soil group. Hydrologic soil group is that A through D classification. So right now we can click on these and we can know inside our watershed what each one of the soil types is, but it doesn't have hydrologic soil group yet. So that when you click Join NRCS Data, then it's going to go in and match up each of the soil types to its corresponding hydrologic soil group. Now there may occasionally be some area that it doesn't have the hydrologic soil group for. And so fill blank values is a way of saying, well, if there's any place that we don't have the data for, then you can just assume that it's soil type, whatever. And so if you want to be conservative, like any location that you don't have a hydrologic soil group assignment for, if you assume that it's D, then that would kind of give you the worst case scenario for runoff. But even if we don't have it fill the blank values, I think in this area all of the polygons have the data that it needs. But we'll do a curve number report and we'll see if there are any areas that don't have values. And then if we have some that were empty, then we can fill the blank values using that. So again, all we did was we right-clicked, join our NRCS data, and then just click OK. And what we're doing across the top here, join hide group, that's the important thing. It's going into one of these other files. If I go into the directory where all this data has been downloaded, you'll see that there is a Morgantown Surgo file, and there's lots of different data files where the 611 is the one that we are working with. That might be in here. Yeah, so here's the WV 611, and the hydrologic soil group is one of these text files that it's going to have to join up to get the correct soil type. So click OK, and now if we do the identify tool again and you pick some polygon in your watershed, you can see now it has a lot more characteristics than it did before. Now not only does it have the 3-letter abbreviation, but it also has some soil properties like the moisture content, field capacity, wilting capacity, but most important to us is the hydrologic soil group. So, there's some that's A, here's one that's C, here's one that's C. So all of these little polygons inside our watershed now has a soil associated with it. So is everybody able to join that soil data? Assignment with them. So when we calculate the curve number, we'll see how much of the area doesn't have a hydrologic soil group assigned. So to compute the curve number, now we're following the steps on the back side of the paper there. We want to, there's a couple of ways to do it. You can create a new coverage. You can see that right now we have a drainage coverage. Well, you can also copy over all of the soil data into a new coverage, or you can compute it straight from the soil type file. Let's, just to save time, try doing it straight from the soil type file. It may crash because we've got a pretty big area, but it saves you from having to trim, which can take a while. So move over to the, let's see, hydrologic modeling module. So here at the top, the hydrologic modeling module. And then under calculators, so that menu option across the top, calculators, what we're going to do is compute GIS attributes. And so we want to calculate curve number, and we're going to use GIS layers. Nope. All right, cancel. We are going to, it used to be a little bit different. All right, we're going to create a new soil type coverage. So starting at the top, right-click on coverages. So the word over here under map data, you see coverages. Right-click, coverage, and click new coverage. And under the coverage type, instead of general, change it to say soil type. So we're going to create a new soil type coverage. And click OK. And so now you'll see that under coverage, now there's a drainage coverage, which is the boundary of our watershed. And then make active the soil type coverage. And what we have to do now is copy over the data into that soil type coverage that we want to keep. So right-click on the soil type and okay, select shapes. They've moved the buttons around. All right, so here's what we do. Under GIS data, select the shape file that has our soil data, and then using the select shapes tool, which is underneath the identify tool, highlight all of the area that encompasses the entirety of your watershed. So once you've selected it, then go up here to the mapping menu. So does everybody have it highlighted in blue? Okay, once it's highlighted in blue, Then you go to this mapping menu and you do shapes to feature objects. So what this means is it's going to take all of the data from this 611 shapefile and copy it into the soil type coverage. And it's only going to do the part that we've got highlighted. So it's just the soil type polygons that are related to our watershed. And a lot of the ones, like if we zoomed out, a lot of the area that isn't covered in our watershed, it's not going to copy over those polygons. All right, so have it say that it's going to go to the soil type coverage, and here's the shapefile. All right, so click Next. And what we want to make sure that it knows is that what it has in the table as a hydrologic soil group, it's going to copy all of that data as SCS soil type into the new soil type coverage that it's creating. So click Next and Finish. And so now it's copied all of that over. We can turn off the 611 shapefile, and now that the soil type is colored and active, you can see that it covers the watershed area. If we go back to our drainage module, then it'll take the soil type stuff, black and white, and we have all of the polygons covering our area. So now we can calculate the curve number because it has land use, which is that National Land Cover Database. It's got the soil type, and so now go into the hydrologic modeling module and calculators and compute GIS attributes. Now, hopefully, it's going to use our soil type coverage for determining soil type. It's going to use the grid data, which is the land use grid, for determining land use. And then the other thing that we have to do is, you can see it has a summary of the table it's going to use to translate all of that into curve numbers. We have to import the .tbl file that you downloaded from MU Online. So click on Import and change it to all files, and it's so the IWW curve number file. And now you can see that it's read in all of the curve number assignments that we want for different land use types. So when we click OK, what it should do is go through a process of calculating the composite curve number, and then it's going to output those calculations into just a text file that it's going to open up with, in this case, since I have it on this computer, the notepad. And so it tells me how much area there is that was developed medium intensity land use with a soil type C, and so then it tells me what curve number it assigned for that area, and then the product of curve number times area. This column is because it's going to determine a weighted average with those details. So at the bottom it says that my watershed has a curve number of 69.6. I see some nodding and some shaking. Let's pause for a moment. All right, so it calculated the curve number, and it copied that curve number into whatever model is initialized over here. So right now it says HEC1. Let's switch it over to TR-55. And if we open up the dialog box for TR-55 by double-clicking in the basin, then hopefully what we'll see is that curve number of 69.58 has been copied in to the runoff curve number area. And it knows the drainage area, so 8.88 miles approximately. We can calculate the time of concentration. So if we go into the basin data and we switch down to the SCS method, it automatically knows the length, the curve number, the watershed slope, and so it's going to calculate and fill in the time of concentration. So in my case, 3.2 hours. The only thing that we'd have to do is change it over to a type 2 distribution, And then we need to find out what is the 24-hour storm for what we want to analyze. So if we want to know, for example, the discharge for a 5-year storm, then we'd go over here to the precipitation frequency data server and find out from Morgantown what is the storm depth for a 5-year storm. Okay, so I've got the crosshairs on Morgantown. Go down here, find the 5-year storm, 24-hour depth, 3.06 inches. And so if I switch here now to 3.06, as soon as I move away from that, it's saying, all right, that the peak discharge is going to be 860 CFS. And let's write that down because we're going to compare the TR-55 estimate. TR-55 estimated that it is 860 CFS for the 5-year storm. Okay? And we can compute the hydrograph and see what that looks like. It's going to determine the hydrograph based on the 24-hour storm event, where that typical shape of the precipitation, like when the storm is happening, is that there's very little rainfall at first, and then there's a big upswing and most of the rainfall occurring at a certain time.